So now let's turn our attention to large-scale structure in the universe. And first, let's review some of the basic observations about large-scale structure and how we get to measure it. This is, of course, a numerical simulation, not the real universe, but it kind of shows what the universe might look like, visible galaxies embedded in this cosmic web of dark matter filaments. So the densities in the early universe serve as seeds for all of us. I will talk about how that happens. And so they fall upon themselves under their own gravity and accrete smaller pieces, and that's how galaxies and clusters and other things form. So on scale larger than galaxies, we talk about large-scale structure. And that could be just general field or groups and clusters and so on, but distinct from galaxies. And when you look at the sky, you don't see just kind of uniform web of matter. You see galaxies as very distinctive little island universes. And the reason for that is important. They actually form with an additional process on top of what drives formation of large-scale structure, which is pure gravity. So the way we map this out is we need to measure distances to galaxies that form large-scale structure. And we do this by measuring redshifts, the velocities of galaxies. You probably know that the universe is expanding, and the recession velocity of a galaxy is proportional to its distance. We'll go through that in more detail later. But the point is that if you can measure the distance, that can be translated into the radial distance to the galaxy. And with the two coordinates on the sky, you kind of know where it is. So in order to map three-dimensional structure in the universe, you need to measure distances. And large surveys that measure up to a couple million redshifts by now have been done. And we have a fairly good understanding of the morphology of large-scale structure. Now, cluster of galaxies is something that was very obvious and visible very early on. But amazingly, it took a long time, until about 1980s, to realize that actually galaxies are not uniformly randomly peppered through the universe with occasional blob like a cluster, but they actually form coherent structures of filaments and sheets and whatnot. So this is the 6,000 brightest galaxies in the sky. And the number was chosen because with the naked eye, on a good sight, perfect vision, you can see 6,000 stars in the sky. Well, in two hemispheres. And so this is plotted in the equatorial coordinates, which remember is just outward projection of Earth's equatorial coordinate system. And so there is a dark band on the sky. Any guesses what it could be? It's called the zone of avoidance, yes? That's correct. It is the dust of the Milky Way absorbing light from the galaxies outside. And as soon as people realized that there is such thing as interstellar absorption, became obvious why this is the case. There are, of course, galaxies behind it just as well. You will also notice that there are some interesting structures and features, and they're labeled here, but here they're shown in more detail. Now, this is in a different coordinate system. This is in a coordinate system, galactic coordinate, so galaxy plane is at the equator. And this is galaxies from 2MASS. There's a 2-micron all-sky survey in near infrared, so it's easier to see through the dust. And some of the important structures are labeled. You can look at this later, but you can see that there is clearly non-uniform distribution. Now, starting from smaller scales, there is the local group, about which we spoke already, and it's our immediate neighborhood, about 2 megaparsecs in size. Milky Way and Andromeda are two big galaxies, and there's a whole lot of smaller stuff around them. And our local group is one of many, many other groups. In fact, most galaxies in the universe are in groups. And we belong to what we call the local supercluster, which is a bigger structure, about 60 megaparsecs, and it's flat, well, it's 6:1 flattening ratio. And it's centered on the Virgo cluster of galaxies, about 15, 17 megaparsecs from us. And it includes some other poor clusters and a lot of other groups which are labeled here and kind of indicated in this quasi 3D plot. So superclusters are the biggest structure we know about. And so far, a number of them have been mapped around us, but in some sense, their boundaries are somewhat arbitrary. Once you get on the scale of hundreds of megaparsecs, you're really talking about describing the overall density field of the large-scale structure. So one of the first large redshift surveys was done at Center for Astrophysics at Harvard-Smithsonian, and they did it then again. And since they couldn't observe enough galaxies to cover whole sky, they used a new strategy. That instead of doing the whole full sphere, they just did cuts. They would do thin slices in right ascension, as sky turns, but very narrow in declination. And that gives you a fair sample of what the universe might be. You're losing one dimension, but you can extrapolate. It's all the same. And they noticed immediately that there are all these interesting structures. They're centered on a rich cluster of coma. There is feature pointing at us, and those have been called fingers of God, pointing at you. We now understand where they come from, but you also see there are all these filaments and voids, and because this is essentially 2D cut through a 3D structure, chances are that what you're looking at really is more like a sponge-like structure. You do a thin slice through a sponge might look like this. So what we're measuring really is not the distance, it's redshift. And that is combination of the actual cosmological expansion velocity, which we could translate directly into distance, but also galaxies have their own velocities that have been caused by gravitational infall. And so in the real space, say if you have a dense cluster of galaxies in it will have velocity dispersion, kinetic energy, and random motions just to balance against the gravitational potential of this massive cluster. You're not observing sideway motion. That's much too slow to see. But you can see the radial component. So that radial component adds to the overall cosmological expansion velocity. And so instead of seeing a round blob in the redshift space, you see it highly elongated by the dispersion of galaxies along the line of sight. And in a thinner and less dense structure, what's happening is that galaxies are still falling in. So galaxies on the far side of it are coming towards you, galaxies on your side going a little extra away from you. That kind of piles them up at the distance of this filament. And so the filaments look thinner than they really are. So both effects play some role, and one can model them exactly. So the field has been really transformed by very large redshift surveys. There were two of them. The first one is called the 2-degree field redshift survey. It's named after the instrument at Anglo-Australian Telescope in Australia. And they measured 250,000 galaxies, not over the entire sky, plus quasars and whatnot. And that was surpassed by the mother of all surveys, the Sloan Digital Sky Survey, which surveyed about a third of the sky and measured redshifts to close to 1 million sources by now. So this is what slice cut through 2DF survey looks like. Now this is going much deeper than the previous older CFA redshift survey. You can actually see labeled on the cone how far it goes, both in terms of redshift and billions of light years. So this is obviously plot for public consumption because astronomers will never use light years, use megaparsecs. And again, you see the same structure goes on and on. Voids and filaments and dense concentrations and so on. But you don't see structures that are bigger than about 100 megaparsecs. And that's about it. Beyond that, it's pretty much uniform universe. The same kind of thing was observed by Sloan Digital Sky Survey, going a little deeper. Again, this is projecting their redshift volume onto two slices in the sky, so there is some smearing. And again, see the same kind of pattern of voids that are typically of the order of tens of megaparsecs in size, and mesh of filaments connecting and ending in clusters of galaxies. Now, to go deeper, there isn't enough telescope time in the world. So instead of that, people do what, say, census studies do. You don't need to ask every American about something. You can only ask representative sample, a few thousand, say. And so The equivalent of that is doing a deep, deep redshift survey in a narrow patch of the sky. And those are called pencil beam surveys. So sort of we drill a thin cone all the way out to large redshifts. And the idea there was to probe galaxy evolution, but turns out also to be constraining structure evolution. And now this has been done, again, on industrial scale. A couple of 100,000 faint galaxy redshifts have been seen. And lo and behold, we see the same kind of structure all the way out. So these are two little slices through one of those surveys obtained at Keck telescope. And they're exaggerated in thickness, because this is a really narrow beam compared to the depth. But you can see that it's intersecting same kind of structures, sheets, filaments, voids, and so on. And if you plot the density, redshift distribution, which is the distance distribution, see the spikes. Every time you cross one of those filaments, you see excess number of galaxies. So it's just like nearby. And this is interesting in of itself.